So today's speaker is Yoon from Autonomous University of Barcelona. His title is Adjoint Reidemeister Torsions on Character Varieties.
Okay, thank you. Thank you for the introductions. Also, first, I would like to thank the organizers for having me here and giving me such an opportunity. So in this talk, I would like to talk about the so-called the adjoint Reidemeister torsions of hyperbolic extreme manifolds and some properties their properties on the character varieties. Okay, so suppose we have any hyperbolic extreme manifolds, then of course there are numerous ways to study these manifolds. And one interesting way is to study the Chern-Simons theory associated to these manifolds. And I'm not going to define what the Chern-Simons theory is, but roughly speaking, when we say we are interested in Chern-Simons theory, in many cases we are interested in character varieties of these manifolds and some hyperbolic invariants defined on the, anyway. So when we say we are interested in Chern-Simons theory, in many cases we are interested in the character varieties of these manifolds and some hyperbolic invariant defined on character varieties. So for instance, hyperbolic volume and so-called Chern-Simons invariants, and of course the adjoint Reidemeister torsion or simply adjoint torsions, which is the topic of this talk. So the reason that the Chern-Simons theory is fascinating is that it is obviously one branch of the geometric topologies, but at the same time is one field in physics. So in particular, the Chern-Simons theory is an example of so-called the gauge field theory. So, so here's the Chern-Simons theory has an interaction with mathematics and physics, in particular the quantum field theory. So in many cases, physicists suggest some conjectures on geometric objects or mathematical objects based on their like quantum physical intuitions or idea, which is highly non-trivial to mathematicians. So here's some examples, conjectures, such conjectures. And today's goal of this talk is to introduce one of those conjectures called the vanishing conjecture. So it was proposed in 2019, so it's quite recently. And roughly speaking, the vanishing conjecture says that the adjoint torsion of hyperbolic extreme manifolds, of course, satisfies a certain type of vanishing identities on the character varieties. And also, I would like to note that these kind of conjectures derive from physics or idea, like intuitions of physicists, are generally extremely hard because their intuition are not intuition for mathematicians. So, so today, the precise goal of this talk is not just to introduce the vanishing conjecture, but also introduce one possible way to attack this conjecture using some technique in complex analysis. Okay, so let me start from some basic definitions. The Reidemeister torsion, or simply just torsion. Okay, so suppose we have an isomorphism of two vector space. Then we all know that if we choose a basis of each vector space, then we can define the determinant of the isomorphism. And of course, this is a non-zero complex number. And viewing this isomorphism as a chain complex of length 2, like this, then we can extend this notion to any acyclic based chain complex. So here acyclic means that the homology of this chain complex is trivial. So it corresponds to the isomorphism here. And the base means that each vector space has a preferred basis in order to consider the determinant. So we can define a certain complex number, a non-zero complex number, which is called the torsions. And the precise definition is as follows. So we first choose some tuples of vectors, so some vectors in each vector space, such that the image of the bound, so here delta I is a map from Ci to Ci minus 1. So the image of this tuple Bi is a basis of the image group, so the subspace of the image. Then one can check that from the fact that this chain complex is acyclic, the image of Bi plus ones together with Bi form a new basis of the vector space Ci. So that means that we have two bases in each vector space. So we can consider the transition matrix between them. And the torsions of this chain complex is defined as an alternating product of these determinants of these transition matrices, which is a non-zero complex number. And one can check that this number does not depend on the choice of these tuples Bi, because the product is given by the alternating products. Precisely, a Bi appears once in numerator and once in denominator. So somehow it cancels out. And furthermore, actually, we can extend this notion to any based chain complex. So that means now we can have non-trivial homology here. But in this case, we have to specify a basis. So now the torsion also depends on the choice of the homology. And the definition is almost same, but we have to put Hi here to get a new basis of the vector space. So of course, we need to put Hi here and H here. So almost same. Anyway, the torsion is an algebraically defined tool, which gives us a non-zero complex numbers whenever we have a chain complex. Okay, so we have a certain algebraic tool. So let's apply it to a geometrical setting. So we first consider a closed hypoxyl manifold. And of course, there are some like sort of standard chain complex whenever we have like manifold, such as like singular chain complex or cellular chain complex. But it turns out that the torsion for those standard chain complexes are somehow trivial. So they don't give you some interesting research. So therefore, we have to twist those standard chain complex using representations. Right, so we are going to consider SL2C representations. So here X is the SL character variety of the irreducible representations. So as a set, X is just a set of the conjugacy classes of irreducible representation of the fundamental. And in many cases, but not always, but in many cases, this character variety has dimension 0. So we are going to assume the case. So please recall that for a closed hypoxyl manifold, the closed manifold has a rigidity, so we cannot deform its structures, and that means that the geometric component of this character variety is always zero-dimensional. And once but here we are assuming that the other components are also zero-dimensional as well. Okay, so we choose now we choose one representation row here and define the twisted cochain complex as follows. So this is a standard construction of twist chain complex. So first we choose any triangulation of manifold so that we can consider like cells in the manifold or the usual cellular chain complex. And then we consider the universal curvature of these manifolds. Then the standard cellular chain complex admits an action, the fundamental group actions through the transformation. On the other hand, this Lie algebra of the SL2C also has a fundamental group action. Since we since we choose the representation, right? So our joint action associated to these representations define actions on the Lie algebra. So we have two phi-on modules, so we can consider homomorphism between them. And this is the standard definition of the twisted chain complex when we have a representation. Okay, so it is well known that this chain complex, this chain complex is acyclic. So the cohomology is trivial. And the important fact to prove this acyclicity is that the first cohomology is isomorphic to the tangent space of the Jarsky tangent space of the character variety. So this is the classical theorem of the Andre-Weil. And since we assume that the character variety is zero-dimensional, so that means that we have a trivial first cohomology. And the other dimension can be proved by like using the Euler characteristic arguments or duality, something like that. So anyway, since we have a cyclic chain complex, so we can define torsions if we choose a basis of this chain complex. And there is a very canonical way to do that. So first we choose a basis of the algebra. So here EJ is a basis of Lie algebra. And here CI is a cell in the manifold. And the tilde means that we choose a lift to the universal curvature. So CI tilde is a lift to the cell in the universal curvature. And one can easily check the collection of this assignment, sending CI tilde to EJ is a basis of this twisted cochain complex. And this is very like standard basis. Anyway, since we have a sort of standard chain basis, we can define torsion of this acyclic chain complex, and we call it the adjoint torsion. So this is non-zero complex numbers defined for each representation. And it is known that this number is invariant under conjugating representation. So invariant under the conjugation. So that means we can define the torsion as a function on the character variety. So it's a map from character variety to the non-zero complex number. And this is our adjoint torsion. Okay. And as I mentioned before, the torsion has an interaction with quantum field theory. In 2019, these three physicists proposed the conjecture as follows. So they this conjecture predicts that for any closed hypoxia manifold, the inverse sum of adjoint torsions over the whole character variety is always zero. So this is very surprising conjecture to mathematicians and even to experts in this field. And as you can see, the title of these papers, it's all about the physics. So everything is written in terms of physics. So actually, there's nothing that I can understand. But fortunately, Dongmin Gang, one of my coworkers, briefly explained what they did in this paper. So he explained that they found for each non-negative integer g, they found this power sum of torsions is coincide with certain number that counts some, I don't know, but some quantum physical states, which is somehow related with this 6-dimensional manifold. And of course, I don't know what it is. But point is that this power, the power sum is number that counts something. So it's anyways should be integers. In particular, when we put g equals 0, left-hand side becomes the inverse sum here, and the right-hand side becomes zeros. I don't know why, but he explained that this surface becomes a sphere, and sphere has a trivial fundamental group. So they argued like there is nothing to count for the right-hand side. So so he explained. He explained a little bit more detail, but I found that it's almost impossible to understand like their intuitions, their logic. So rather than that, we just tried to extend these conjectures to manifold with boundaries. And of course, we can have many boundaries, but for simplicity, I will assume there is only one. So now our manifold is compact unit manifold with a single torus boundary. And of course, the interior has a nice hyperbolic structure. And once again, we considered SL2 character variety of reducible representations. And in this case, usually this variety has dimension 1. Please recall that we have, if hyperbolic manifold has a torus boundary, then we can deform hyperbolic structures along this torus, right? So that means the geometric components is always one-dimensional. So it's reasonable to assume that this character variety has one dimension. And then we have some problems to generalize the conjecture. The first one is that our twisted chain complex is not acyclic. So please recall that the first cohomology is isomorphic to tangent space of the character variety, but now it has a dimension 1. Right? So since we have non-trivial cohomologies, so we have to choose a basis of this cohomology to define torsion. And in 1997, fortunately, Porti proved that if we choose a curve, a simple closed curve on the boundary, then there is a natural way to choose a basis of this cohomology, twisted cohomology. So that means we can define the torsions, but it depends on this curve mu. So now torsion depends on a curve. And the second problem is that we cannot do the sum over the whole character variety because it has positive dimension. So it's infinite set. So to get a finite sum, we have to make a slice of the character variety, and the natural way to do that is using the trace function. And moreover, since we fixed a curve mu, we can use the trace function of the mu. And generically, the level set of these functions is a finite set, 0-dimensional. Of course, there could be some bad points, but for generically, the level set is finite sets. So we thought that this statement is a natural candidate for a manifold with single torus boundary. And of course, we checked this is true for several examples. And after that, Dongmin told me that he has some quantum physical argument to supporting this conjecture. So far we believe this is true. And once again, actually, we do not have any like mathematical or geometrical intuitions why this kind of equation should be true, or what's going on behind of these conjectures. So actually, many thing is unknown so far, mysterious, but at least we know some partial research. So so far we know that these conjectures are true for some examples. So the previous conjectures are true for closed hyperbolic linear manifolds obtained from the figure in knot by Dennett-Bailey. So this gives us an infinite family of hyperbolic closed manifolds. And for boundary cases, we know that this is true for twist knots, whose diagram looks like this. And even more complicated knot called two-bridge knots. So their diagrams looks like a little bit more complicated. Recently, Tran and Yamaguchi proved that this is also true for once punctured torus bond. Some families of once punctured torus bond. And actually, the key idea of this proof, these theorems are essentially the same. So from now on, I'd like to briefly introduce the technique, the key idea. But before that, let me make some remark on the conjecture. So the first one is we need the hypothesis conditions. So that means for some reason, if we remove the hypothesis conditions, the conjecture fails. So for instance, the torus knots is the simplest examples of non-hyperbolic knots. But of course, we can define torsion of these knots exactly same way, in the same way. But if you compute the inverse sum, like that, it does not give you zero. Of course, this is integer, but does not give you zero. I think it's like plus minus 2 or something. And the second thing is that we have to consider all components of the character variety. So for instance, the character variety of knot 7,4 or 9,23 has two components. But if you compute the inverse sum over either one of them, the sum does not give you zero. So to get the zero, you have to consider both components. And actually, this is quite interesting to me because when we say we are interested in hyperbolic manifolds, obviously we are interested in like geometric structures. And in terms of character variety, we are interested in geometric components, right? Because they give some geometric structure. But this conjecture says that to get right conjecture or to get right intuition, we have to consider all components of the character variety, even though the other components does not give you like genuine geometric structure. And I think this effect makes the conjecture a little bit more fascinating. Okay, so anyway, now let me introduce a possible way to attack this conjecture using global residue theorem. So the global residue theorem is a very classical theorem in complex analysis, and it says that if we have complex manifolds with a top dimensional metamorphic form, then the sum of the residue is always zero. So here, actually, residue is non-trivial, is 0 if P is not a pole. And since there is only finitely many poles, so actually this sum is a finite sum. So it's well-defined sum. And here are some examples, typical examples of the global legit theorem, which is quite familiar to us. So for instance, if we have a one polynomial in single variable, we can consider Meromfi form 1 over fx dx defined on CP1. So not just C, but CP1 because we have to compact manifolds. And if this polynomial is generic in some sense, then the global legit theorem says that the sum of 1 over f prime, the derivative f, over all zeros of f is always 0. So I think this is also known as the Euler-Jacobi theorem, or maybe simply Jacobi theorem. And also, there are a multivariable version of this. So for instance, if we have n polynomials in n variables, then we can consider this form on CPN. So here h is another polynomial in n variable. And once again, if these polynomials are generic in some sense, the global rigidity theorem says that this kind of sum is always 0 if the degree h is not too big compared to the degree of f. Okay, so so here the common zero set of f describe where this form has a pole, and here the h over the Jacobian term is the residue of this form at the point, and that these degree conditions guarantees that this form does not have a pole outside of Cn. So it's an infinite point. So that guarantees that when we consider this common zero set, we don't have to worry about the infinite point. So actually, this common zero set is taken in Cn. Okay, so this is some typical examples of global legit theorems. And the reason why I think this is an appropriate tool to attack our conjectures is as follows. So let me focus on a manifold with torus boundary. So our character variety has a dimension 1. Anyway, this is a variety, so we can consider its defining equation in some dimensions. So if we have n variables, then the generically the number of defining equations should be n-1, right? So the character variety has, so that the dimension of the character variety is 1. And then this level set of trace function is given by the common zero set of n functions, where the lost function is just the trace function of the curve mu. And I found out that in many cases, if we compute the torsion explicitly, then we can find the Jacobian term of this system as a factor of torsion here. So actually, this means nothing, because whenever we have A and B, we can always write A is equal B times A over B. Right? So actually, mathematically, this equation does mean nothing. But the point is that the other factor is relatively simple, so that we can apply the global rigidity theorem. So, what I mean by that is that if we re-express the inverse sum of torsion using the system that we choose, so here the level set becomes the common zero set of F, and 1 over torsions becomes something over the Jacobian, right? And the global rigidity theorem says that if we can control the degree of nominator, so if the degree of nominator is not too big, then global rigidity theorem says that this sum should be 0. And of course, we are ignoring many technical details, right? So actually, we have to check that these polynomials are generic in some sense, but I'm not gonna tell the like technical details. So anyway, this is the idea to check these conjectures, and let me a little bit explain more how it works in examples. Okay, so twist knot is a knot in S3 whose diagram looks like this. So we can have many crossings here in the bottom. So this is an infinite family. And it is known that this manifold is hyperbolic if there is more than one crossings in the bottom. And if there is only one, that this knot is called trefoil knot, and this is non-hyperbolic knot. And the character value of these knots, twist knots, are computed by Riley in 1970s. So he showed that the character value is an algebraic curve in C2. So the defining of equation of this variety is single polynomials in 2 variables. So he also showed that how we can compute this polynomial f. And I found out that if we compute the torsions, we have the Jacobian term factor here. And as you can see, the other factor is not that complicated. Right? And here, actually, I use an eigenvalue function instead of the trace function. But since we are working on SL2C, trace and eigenvalue are essentially the same. So so they are essentially the same. So anyway, the key point is that the other factor is not. We can compute the degree of this the other factor. So we can deduce the conjecture. So we can prove that the conjecture is true for all hyperbolic twist knots using the global rigidity theorem. Right? An interesting thing is that when n equal to 1, so when the knot is trefoil knot, the degree condition fails, so that we cannot apply the global rigidity theorem. And this is quite surprising to me because the hyperbolic condition is the geometry condition, obviously. But everything written here is algebraically defined. So torsion is algebraically defined, character value, eigenvalue, everything is algebraic object. But somehow the geometric conditions, the condition that manifold has hyperbolic structure, can control this degree of algebraic objects. I don't know how it can be possible, but I found that this phenomena happens even more complicated knots called two-bridge knots. So two-bridge knots is also a knot in S3 whose diagram looks like this. So it's a little bit more complicated. In fact, the twist knot is a subfamily of two-bridge knots. So the computation becomes further complicated, but the point is the basic idea is the same. So if we compute the torsion, we can find the Jacobian terms, and we can control the other factor. So, and once again, if a knot is hyperbolic, then we can check that the degree condition satisfies, so that we can prove the conjectures by using the global legit theorem. Okay, so and then I have to remark that Tran and Yamaguchi show that the conjecture should be slightly modified. So they compute some examples whose character variety has a special component. So special components means that some trace functions is constant on that component. And they found out that if you compute the inverse sum for these examples, the sum does not give you 0. But if we exclude these special components, the sum give you a 0 again. So based on this computation, they modify the conjecture by using not the whole character variety, but exclude some components where the trace functions is constant for some boundary curve. So as we saw, these conjectures are derived from physics, some ideas in physics, and physicists indeed they give some non-trivial conjecture, but they don't care that much about the details, like technical details or rigorous definitions, as much as mathematicians do. So so in many cases we have to slightly modify like this. So, and I think this is fun because physics suggests some conjectures and mathematicians add some details, and physicists to reconsider why those conditions should be required or the meaning of those conditions in physics. So anything is all about the interaction. So I think this this interaction is a fun. Okay, and the last 5 minutes, let me discuss a little bit more about the conjecture. So far we focus on a manifold with torus boundary, whose character variety has dimension 1. And of course, there are some examples whose character variety has a higher dimension component, so dimension greater than 1. And we can try to generalize the conjecture for those manifolds, but there is some problems. So first, we don't have definition of adjoint torsion. So please recall the first cohomology is isomorphic to the tangent space of character variety. And for instance, if the character variety has a dimension, let's say 10, then the first cohomology is the vector space of dimension 10, and we have no geometrical intuitions to choose how to choose a basis of this 10-dimensional vector space, right? So the first problem is we don't have definitions, and second one is, once again, this sum does not make sense, as this level set has positive dimension, as the dimension of character variety has a dimension greater than 1. So once again, this becomes infinite, so it makes problem. So anyway, the examples of higher dimensional components can be obtained by the connected sum. So if we have two knots, K1 and K2, and if we remove some small part of both knots, and if we join these two knots like this, then we can obtain a knot. Looks like this. And it is known that the connected sum never give you hyperbolic knots. So this is always non-hyperbolic. But it has the character value of this knot has a component of dimension 2. And moreover, if we do the connected sum of several knots, so n knots, then the character value has a component of dimension n. So even though this manifold has a single torus boundary, the dimension could be higher. And then Porti and I show that actually there is a natural way to define other torsion for this connected sum. So the reason that this connected sum has a higher dimensional component is that there is because it contains some essential torus. So here the blue surface is actually torus, which is non-trivial in some sense. So we call it essential torus. And we found out that there is using a standard Mayer-Vitré sequence, we found out that there is a map from a zeroth cohomology of sigma to a first cohomology of a manifold. And as I said before, this first cohomology has a dimension 2, so we have 2 directions. And the one direction is determined by the curve mu, like before. And we found out that the other direction is determined by the image of this zeroth cohomology of the essential torus. So, so using this fact, we found out that there is a natural definition of the torsion. So once again, it's a function on the character variety. And more importantly, we found out that this is locally constant on the level set of trace function. So that means that even though this sum is an infinite sum, but it makes sense if we take one representative on each component of these levels, because it's locally constant. And we proved that this connected sum not satisfy the conjectures if every single component, every component satisfy the vanished conjecture. So in particular, we can say that the connected sum of 2 bridge knots always satisfy the vanished conjecture, even though it is not hyperbolic knot. Okay, so that's what I prepared for today. So thank you for attention.